Hello again, everyone. Welcome to our discussion of section 4.6. In this section, we will discuss solving polynomial inequalities and rational inequalities. A very detailed subject with detailed calculations. So that brings me to my usual reminder to ask you to please skim through the section 4.6 before you watch this video. In this, I usually ask you to take 30 minutes to 45 minutes to do this. Maybe in this case, maybe it's well worth it if you spend an hour and even an hour 15 minutes to look at the book and the examples that have been solved in the book. It's well worth it. And then watch this video and take notes of anything that may be important to you or any persisting questions that you might have. So watch this video and attend the class in order to make sure that you understand the subject fully. And then please review your notes and go over the solved problems in the book. Don't look at the solutions in the book. Solve them on your own to see if you get the same results. Do the same with the examples you see me go over in this video. Pause the video, solve it on your own, and then look at my solutions. And then, of course, complete the homework after you've done that. Complete the homework by the due date, and of course, review the previous material, which is to say, spend half an hour a week on a review of anything we've covered so far. And if you do this regularly, really that's all it takes. It's half an hour of refreshing your mind if you do it regularly. But if you skip a few weeks or even a couple of weeks, then it's going to take you a lot more time to refresh your mind about the stuff we've covered before. When we solve polynomial inequalities or even rational inequalities, there are values for which the expression, whether it's a polynomial or it's a rational inequality, there are values for which these expressions are either 0 or undefined. Undefined polynomials are always defined, right? We learned that before. So polynomials are defined everywhere in the plane. But there are points where they are equal to 0. So we're going to be looking for those values where the polynomial might be 0. With respect to rational inequalities, then we're going to have points at which the rational inequality is equal to 0. And we're going to find points where the rational inequality is undefined. So we're going to look for those two numbers for rational inequalities. So what is the use of these numbers then? The numbers that would make a polynomial 0 or make a rational inequality 0 or undefined. What's the point of this? See, as you can see on the screen, these are inequalities that we're solving. Inequalities have infinitely many solutions. So in order for us to figure out infinitely solutions, we need to narrow down the regions of the plane or the real number line, in this case, real number line, that where the solutions exist. There is no way for us to be able to spend even our lifetime will not be enough to find all the solutions of an inequality if we don't have a way to divide the solution region into possible solution regions and then test each region for valid solutions of each inequality. So we need to, in order to save time, in order to be able to make this task a practical one, we need numbers that would divide the real number line into testable regions. So if you have, say, x equals -1 and x equals 3, suppose, that would make a polynomial equal to 0, let's say -1 and 3, positive 3, would make a polynomial equal to 0, then those two numbers divide the real number line into regions. Let me just use my scratch paper. Before we go back to the worksheet, I'm going to use my scratch paper to make this point. So suppose we have x equals -1 and x equals 3. Suppose these two numbers make a polynomial equal to 0. Otherwise, i.e., we have a name for that, right? i.e., they are the zeros of a polynomial. Okay, then these two, the nice thing about this number is that in an inequality format, right, like that, they divide. So suppose the inequality for which, the polynomial inequality for which these make the polynomial equal to 0 is like that. It's formed like that. So then we have -1, and then we have 3, and then we have -infinity to infinity. So if we didn't have these numbers, and I will call them boundary solutions. They are the zeros of a polynomial, but because of the way we're going to use these numbers, I'll call them, it's more suitable if we call them boundary solutions. Right? So these become boundaries. Boundaries of what? Boundaries of regions that we can check. So we can check here, we can check here, and we can check here. Then why is this useful? This is why it's useful. If you test one number in this region to see if the inequality is valid at that point, then that result is valid for all numbers in that region. So you don't need to spend, and there are infinitely many numbers in each region. There are infinitely many numbers in this region, infinitely many numbers in this region, and infinitely many numbers in this region. Do we have even enough time in our lifetime to test all these numbers in each region to see if they're valid? No. But the nice thing about boundary solutions, and these are numbers for which the polynomial or a fraction is equal to 0 or undefined in the case of fractions, undefined also, they give us these regions to test. So if all you need now is test one number, not infinitely many numbers in that region. If that number does not check out, then none of the numbers in that region check out. None of the numbers in that region are valid. If you test a number in this region and it checks out and it's a valid result, then all numbers in this region, all the infinitely numbers in this region will make this are a valid substitute in this inequality, or a solution of that inequality. If you test one number in this region and you get some kind of a result, whether it checks out or it doesn't, that result applies to all numbers in that region. So what I've just explained is the big picture idea, what we're going to be doing for this entire section. And it can get pretty tedious and meticulous, but that's why I ask you to read the section before you watch the video, so your mind is prepared for what's coming up, for this level of detail. Okay? Okay, having said that, those boundary solutions that I just spoke to you guys about, your book, the author of your book calls them critical values. So I'm also using that term that term to indicate, to make sure that you are familiar with both kinds of terminology. Critical values are the same thing as boundary solutions, no different. Okay? So the first task before we solve any of these inequalities is to find the critical values or the boundary solutions. Without them, we cannot solve any of these. As I said earlier, because our lifetime is not going to be enough to find all the solutions possible. So we need to narrow down the real number line to regions where we can test one single number, not infinitely many numbers, in each region. And that's very much practical, right? Okay, so this one is a polynomial, right? This is not a rational inequality. We'll get to those later. This is a polynomial. So with respect to polynomials, we've learned that we need to factor them. So this is an easy polynomial to factor. We can quickly factor this in our head, right? Because these numbers are pretty easy to deal with. We can say that the factors of this polynomial are x plus 5 and x minus 3, right? Greater than 0, right? X times x, x squared. And 5 times minus 3, minus 15. Where is the 2x coming from? From 5 times x minus 3x, which will give us positive 2x. Okay? All right, so why did we factor this? Because we can now find the zeros of this polynomial. So let's do that. So x plus 5 equals 0, x equals negative 5. That's one of the zeros. That's one of the critical values. That's one of the boundary solutions. And then x minus 3 equals 0. Therefore, x equals 3, right? We're solving for x from each factor. Okay, so now let's see how, let's draw this. Let's draw a picture to make these things more clear or clearer. Negative infinity to infinity, with the 0 in the middle. So the solutions, these two numbers will make this polynomial equal to 0. But according to this inequality symbol, is 0 an acceptable result? No, because the left side, notice that the left side cannot be equal to 0. Otherwise, we would have an equality symbol right underneath this inequality. So if I say that this is negative 5, and this is 3, I'm going to put a hollow circle there and a dashed line over it, meaning that the minus 5 and 3 are not acceptable results. But what's the use of them then? The use of them, as you can see, they divide the real number line into regions where we can test. 3 regions for us to test. Okay, so let's test. In each region, all you got to test is the easiest number. Take an easy number in this region. We know negative 5 and 3 are not acceptable, so these two are not. But we're testing the regions in the middle or on the sides here. So testing x equals negative 6 would be in this region, right? And all we need to do is test one single number in each region. So test x equals minus 6 in this region, right? So what do we get? Putting it here in this inequality, we can put negative 6 in either one, that one or this one. But it's easier if you put that in the factored form. So we say negative 6 plus 5 times negative 6 minus 3. And we're asking if the left side is greater than 0. Okay, let's see. Negative 6 plus 5, negative 1. Negative 6 minus 3, minus 9. Is that greater than 0? Minus 1 times minus 9 is positive 9 greater than 0. Yes, it checks out. So yes, this region, all the numbers in this region, all infinitely many numbers in this region are part of the solution. So let's test an easy number in the middle here, in this middle region. Well, the easiest number is 0, so let's see. So test x equals 0. Okay. Once again, I'm going to plug into this one. So 0 plus 5 times 0 minus 3. We're asking if the left is greater than 0. So that is 5 times negative 3, negative 15, greater than 0. Is that statement true? Is negative 15 greater than 0? No. So it did not check out. We picked an easy number here, a test number here, and it did not check out. So that region between negative 5 and 3 is not a solution of this polynomial inequality. So let's test the number here in this region. Let's test x equals 4. Okay, plugging in here, we have 4 plus 5 times 4 minus 3 greater than 0. So we have 9 times 1 greater than 0. Is that true? 9 greater than 0. Is this conclusion or result true? Yes. So once again, we have found a solution region. Okay, so they're asking us to write the answer, the final solution, using the interval notation. Okay, so let's do that. So the solution would be from negative infinity to negative 5, parenthesis or bracket. Which one? Parenthesis, right? Negative 5 cannot be part of the solution because the left side cannot be equal to 0. It can be greater than 0. Okay? So that's one. And in the middle we have no solution, but on the far right side we do. So union, parenthesis, right? 3 is not part of the solution. Parenthesis 3 comma infinity, parenthesis. So there we have our solution region for that polynomial inequality. Okay, do you see now how the critical values or boundary solutions, they are effective in finding the solutions of these kinds of problems? So they are essential. Without them, we have infinitely many numbers to check. Okay, this one. So you've seen one example now at least, and I'm sure if you read the book, you would have seen at least half a dozen examples there. So go ahead, pause the video, and solve this polynomial inequality on your own. And then come back to the video when you're done. Okay, so I'm assuming you've done that, and now you're back. So the first thing is I would want to find the zeros of this polynomial, right? Because like before, those are the critical values or the boundary solutions that will help us divide the real number line into regions where we can test and check for our solutions. So factoring this, we can have x cubed times x squared minus 9 less than or equal to 0, right? Remember, factoring is the opposite of the distributive property. So if you want to verify this factoring, just redistribute this x cubed into these two terms. You should get the original terms back. X cubed times x squared. The bases are the same entity, x, that means when you multiply them, the powers get added. So 3 plus 2, 5. X cubed times minus 9, minus 9x cubed. So we got it. So this is one factor, but should we stop? No. Can we factor this even more? Yes, we can, right? This is a perfect square minus a perfect square. And in the previous lessons, I've talked about which special product formula we can use for that. So let's use that. We have x cubed times x plus 3 times x minus 3, less than or equal to 0. So that's the full factorization of the original expression, okay, original inequality. This is nice. Why? Because now we can find the critical values, the boundary solutions. Let's find them. So if x cubed is equal to 0, then x equals 0. So that's one of the boundary solutions. If x plus 3 equals to 0, then x equals negative 3 is another boundary solution. If x minus 3 equals 0, then x equals to 3 is another boundary solution. Okay? All right. So let me put the graph here. We don't have to graph, but I do it just to be clear about what is going on. Negative infinity to infinity. We have 0 in the middle here. So these are our critical values, these three. So we have 3. By the way, are these values, can they be included as part of the final solution? Yes, they can. Why? Because the left side can be equal to 0. And we know at these values, this polynomial is equal to 0. So these values can be part of the solution. Okay? So that's why I'm going to plot them with a filled-in circle at 0. Then negative 3. Then positive 3. Okay, so this time I'm not going to put a dashed line like I did above, right? Dashed line means those numbers are not included. Negative, and also the hollow circle says the same thing. So this time I'm going to put solid lines over all three, meaning that these numbers are acceptable solutions themselves. But also, we have these intermediate regions to check, right? We need to check this region, this region, this region, and this region. 4 regions to check. So let's start here. Let's test some number in this region, x equals negative 4. Right? And let's put them in here, in this inequality. You can try them here, but this would be easier because all we're looking for is for the sign. Is it less than or equal to 0? Is it some number, negative number or not? So negative 4 cubed times negative 4 plus 3 times negative 4 minus 3. We're asking if the left side less than or equal to 0, if it's some negative number, that is. So negative 4 cubed, that would be some negative number, right? So it would be negative 64. Negative 64 times negative 1 times negative 7, less than or equal to 0. So we have, what do we have? We have, let me get my calculator here. So negative times negative times negative, it's all negative. negative 7 times 64, negative 448, right? So negative 448, is it less than or equal to 0? Absolutely. It's a negative numbers, right? So it must be less than 0. So this region is yes, it checks out. Let's pick a number in this region between negative 3 and 0. The easiest number would be negative 1. Plug it in here. Negative 1 times 2 times negative 4. We have positive 8. Is this true? Is 8 less than or equal to 0? No. So no, none of the numbers in that region are going to be part of the solution. Okay. So let's test the number in this region. Let's test x equals 1, the easiest number. I'm plugging in here. What do we get? We get 1 times 4 times minus 2, minus 8 less than or equal to 0. Is minus 8 less than or equal to 0? Yes. So that region checks out. Yes. Let's pick a number in that region. X equals 4. Once again, we're plugging in here. So this would be 64 times 7 times 1. And if we multiply those numbers, these numbers, 64 times 7, positive 448. Is this a true statement? Is 448 less than or equal to 0? No. Right? So no, that region is not a solution. So what is the solution region then? The solution region, using interval notations, it's going to be from negative infinity to negative 3. Should I use brackets or parenthesis? Negative 3 is part of the solution, so bracket, union, then again between 0 and 3. So 0 and 3 are part of the solution as well as any number in between, right? So bracket, 0, comma, 3, bracket. And that is the final solution. Okay. I hope this is starting to make sense, if it didn't already. Here, this is pretty nice because the polynomial we have is already been factored. So all we can do is immediately go and find what would make this left side equal to 0. So x plus 3 equals 0. We're going to find the boundary solutions, right? Or the critical values, as your book calls them. And then x equals minus 3. Equals 5. And then here is the graph for us to look at. Negative 3 would be somewhere here. I'm going to put a hollow circle. Notice that this is a strict inequality. So the left side cannot be equal to 0. So negative 3 and 5 are excluded from the solution. For that reason, I put hollow circle and I put a dashed line over each. So we have these three regions to check, right? All right, let's test this region, some easy number. We're going to test x equals negative 4. I'm going to plug in there, negative 4 plus 3 times negative 4 minus 5. So we have negative 1 from here, negative 9 from here, less than 0, positive 9 less than 0. Is that conclusion valid? No. So this region is not a valid part of the solution. Let's test some easy number in the middle. So x equals 0. Plug it in there. We have 3 times minus 5 less than 0, negative 15 less than 0. Is that a valid conclusion or result? Yes. So this region is a valid solution region. Let's pick a number, easy number in this region to test. So we can test x equals 6. Again, plugging in here, we have 6 plus 3 times 6 minus 5 less than 0. So we have 9 times 1 less than 0, right? 9 less than 0. Is that a valid result after we picked x equals 6 as to test? No, right? 9 is definitely greater than 0. So no, that region is not a solution. So looking at that, we can write the solution for this problem. The solution is anything between negative 3 and 5, excluding negative 3 and excluding 5. Like that. Okay. Okay, this looks like, looking on the left side, this looks like a quadratic inequality. So if you haven't already solved this on your own, please pause the video, solve this on your own, and then come back to the video. Okay, I'm assuming you've done that, and now you're back. So first thing I would do, I would move everything to one side and combine the like terms and simplify the expression as much as I can. So x squared plus 4x plus 7. I'm going to move 5x from the right side to the left. When I do that, this 5x changes algebraic sign from positive to negative. I'm going to move 9 from the right side to the left, minus 9 greater than 0. Okay, so x squared, now let's combine 4x minus 5x, that's minus x, 7 minus 9 minus 2 greater than 0. Okay, this is an easy expression to factor. We have x times x, x squared, minus 2, so minus 2 and plus 1. 1 times minus 2, minus 2. And minus 2x plus x, it's minus x. So this is the correct factors. These are the correct factors of that expression. So let's find the critical values, right? The boundary solutions. So x plus 1 equals 0. So we know the left cannot be equal to 0, right? Because the left side cannot be equal to 0, these critical values should be excluded from the final solution. Okay, so then let's draw the graph for this one. So -1 would be somewhere here. I'm going to put a hollow circle there and dashed line over it, because the left cannot be equal to 0. And -1 would make this expression 0, but we cannot have x equals -1, because the left cannot be equal to 0. It can be greater than 0, but not equal to it. And then 2, another hollow circle here, like that. So we have 3 regions to check. Let's test some easy number in this region. Test x equals -2. Let's plug it into this inequality, this one. It's easier to check here. You'll get the same result if you check these numbers here even, or even here. But it's easier if we check this number in the factored form. Right? Plugging in for x with -2. -1 from here, -4 from here, and this is +4 greater than 0. Is this result a valid result? Yes. Right? +4 is definitely greater than 0. So yes, this region is a solution of that polynomial inequality. Okay? Let's pick an easy number in this region, which would be x equals 0, right? Plug that number here, 0 plus 1 times 0 minus 2, like that. So this is 1 times -2, -2 greater than 0. Is this a valid result? Is -2 greater than 0? No. So that region is not a solution of that polynomial inequality. Let's test an easy number in this region. So I'm going to plug that 3 here. We have 3 plus 1 times 3 minus 2 greater than 0. So this will be 4 times 3 minus 2 is 1. Greater than 0, 4 is greater than 0. Is this result valid? Is 4 greater than 0? Yes, that's a valid result. So yes, that whole region is part of the solution. Okay, so now we can look at that and write our final solution in terms using the interval notation, right? So let's do that. So the solution is that region, -infinity to -1, parenthesis or bracket, parenthesis, right? Because -1 is not included. Union, that region is not a solution. This region is. Parenthesis 2, comma, infinity, all of that region. So that's the solution of that polynomial inequality. All right. Here we have another polynomial inequality. In fact, this is a quadratic inequality, right? So let's solve for this. To solve for x, we need to have these two terms isolated, so 11 greater than or equal to x squared. I prefer, so it was minus x squared on the left, I moved it to the right, it became positive, right? Positive x squared. I prefer to have my variables on the left side, So x squared less than or equal to 11. Okay. Now let's take the square root of both sides. But now we have plus or minus square root of 11, right? By the square root property. The other side, as long as the other side does not represent distance, radius of a circle, or some kind of distance, it must be plus or minus. If it does represent a distance or the radius of a circle, you just toss out the negative one and accept the positive one, positive version. So what do we have here? We have x less than or equal to plus or minus square root of 11. Okay, what is the square root of 11 anyway? It's 3 something, right? 3 times 3 point something. So square root of 11, 3.32, right? Let's say 3.32 plus or minus. So that, let's draw the real number line here. So negative, if this is, well, let's say this is negative 11, negative, and we, the left side can be equal to, should be less than 11 or equal to it, right? So we can put a filled in circle here and a full filled in circle here. This is negative square root of 11, or just like what we calculated, negative 3 point, almost, right? Almost negative 3.32. This one would be positive square root of 11, or almost 3.32. Okay, so let me put a solid line on top of these. So negative 11, square root of 11 and positive square root of 11 are going to be part of the final solution. We know that, okay, because the left side can be equal to 0. Now we need to test each region here. Okay. There are other ways of doing this, but I thought to be consistent with what I've been showing you so far, let me take this route. But we already know that the solution should be in the middle. But I wanted to take you through the same path that we've come solving the previous couple of examples. That's all. But we know this in the middle should check out and these two should not. Okay. So test this region. Test x equals something to this, like negative 4. X equals negative 4. Right? And plug it in here. Negative 4 squared in this one. Negative 4 squared, that. So this would be positive 16 less than or equal to 11. Is this a valid result? No. 16 is not less than or equal to 11, so no. Right? Pick an easy number here, 0. Plug in here. 0 squared less than or equal to 11. Is that true? Yes. So yes, this middle is a part of the solution. Pick an easy number there. Let's say x equals 4. And plug in here. So we have 4 squared less than or equal to 11. 16 less than or equal to 11. No. That is not a valid result, right? So no. Okay, so what is the final solution? The final solution is between and including negative square root of 11 and square root of 11. So bracket, because the negative square root of 11 and square root of 11 are included. Negative square root of 11, comma, square root of 11, close bracket. Okay. So you can see why, I mean, less so in this example, but from the previous examples, you can see how the critical values are so important in identifying the solution regions. And I've called them boundary solutions too. Okay, so this one, if you haven't done this already, please pause the video, solve this quadratic inequality on your own, and then come back to the video to compare your solution with mine. Okay? All right, so I'm assuming you've done that and you've already given your own mind to generate its own solution. If you've done that, wonderful. Okay, so first thing, move everything to one side and set the other side equal to 0. So we have x cubed. Let me bring this to the left. So it was positive on the right side. When I bring it to the left, it becomes minus 3x squared minus 9x plus 27 greater than or equal to 0, right? We brought 3x squared to the left. Now what do? We need to factor this, right? In order to find the critical values or boundary solutions, we need to factor this expression. What technique, do you guys remember what technique we learned in the past that is applicable here in order to find the factors of this expression? Do you remember what technique that was? Can I give you a hint? We have 4 terms that we need to factor. Does that jive, kind of jog your memory? Well, with 4 terms, factoring by grouping may be possibility. So let's pair these 2 in a group and these 2 in a group. And from each group, let's factor the terms that we can factor. So x squared, I'm going to factor x squared. What number do I need, or what term do I need to put here to multiply by x squared in order to get x cubed? Well, just x. Then minus, what term do I need to put here to multiply by x squared to get minus 3x squared? Just 3, right? X minus 3. If you redistribute this x squared into this parentheses, you should be able to get that result, right? And then minus 9, factor minus 9 from these 2 terms. What should I have here in order to multiply by minus 9 and get minus 9x? Just x. What should I put after x such that if I multiply it by minus 9, I get positive 27? Well, minus 3. Greater than or equal to 0, right? So let's step back and visually scan this result. Is there anything else we can factor out? There is, isn't there? The x minus 3 is common to this term, and x minus 3 is common to this term. So let's factor x minus 3 from both. So x minus 3 factored out. What should I put here such that if I multiply by x minus 3, I get x squared times x minus 3? Well, x squared. Minus is minus. What should I put after this minus such that if I multiply it by x minus 3, I get 9 times x minus 3? Well, just 9. Greater than or equal to 0, right? Can we stop the factoring there, or can we do more? What do you think? We can factor more, right? If you notice, this second parenthesis is x squared minus another term squared. So it's a perfect squared minus perfect squared. So we have a special product formula for this, right? Which I've asked you to memorize, please. So let's use that formula to expand and factor this even more. So that's because that's to our advantage. Because we're going to be able to find the critical values easier. We could still find it from this, but let's find all the factors for all the terms. So x minus 3 times x plus 3, right? This one becomes x plus 3 times x minus 3 greater than or equal to 0. Aha! So now we have x minus 3 and x minus 3. Let's combine those two because they're really the same factors. So we have x minus 3 squared times x plus 3 greater than or equal to 0. So this is our result after manipulating this polynomial inequality so far. Okay, this one, that one. Okay. All right, so now that we have that expression in fully factored form, let's find the critical values, i.e. the boundary solutions. All right, let's do that. So x minus 3 equals 0, then x equals 3. X plus 3 equals 0, then x equals minus 3. Okay, so these are the two critical values. Let us draw the graph for this, minus infinity to infinity, negative 3 and 3. These two critical numbers, are they themselves included in the final solution? Yes, because we have greater than or equal to 0, right? We know these two values will make this expression on the left equal to 0. And this symbol tells us that we are allowed to have this expression equal to 0. So negative 3 and 3 themselves, these two solutions themselves, will be part of the final solution. So we have to check, all we have to do is check 3 regions now, right? Okay, so let's test some number in this region. Test x equals negative 4, okay, in this inequality. So we have negative 4, negative 3 squared, negative 4 times negative 4 plus 3. So let's do the algebra on this. Negative 4 and minus 3 is minus 7. Minus 7 squared is 49. Minus 4 plus 3 is minus 1. So we get minus 9 greater than or equal to 0. Is this result a valid result? No. Minus 49 is less than 0, not greater than or equal to. Right? So no, that region cannot be the solution. Let's test some easy number between negative 3 and 3, and of course 0 is the easiest number. So let's plug in this expression for x with 0. So 0 minus 3 squared times 0 plus 3. What do we have here? We have minus 3 squared, that's 9. 0 plus 3 is just 3, or like that, and then 27 greater than or equal to 0. Is this a valid result? Yes. 27, positive 27, is definitely greater than or equal to 0. So yes. Let's test another number in this region. The easiest one would be x equals positive 4. Again, we're going to plug in here. So 4 minus 3 squared times 4 plus 3 greater than or equal to 0. So 4 minus 3 is 1. Positive 1 squared is 1. 4 plus 3 is 7. Greater than or equal to 0. right? All right, so we have 7 greater than or equal to 0. Is this a valid solution? Yes, right? 7 is definitely greater than 0. So yes, that's also a solution. So our final solution is, looking at this graph, what do you think it is, the final solution? The final solution is parenthesis or bracket, starting from here that way. It is bracket -3, comma, 3 is also accepted, right? When we hit 3, this expression, or that expression that is off the screen right now, the one that I highlighted, is going to be 0, so it's acceptable. So that is included, and all the way to infinity. So -3 comma infinity parentheses. Oops. Like that. Okay. All right, so we get to, all the examples we've done so far were about polynomial inequalities. Now we get to rational inequalities. Still, we need to find the critical values. But in this case, the critical values fall into 2 categories. One, as before, these are any values that would make a rational expression like that equal to 0. So we still have that. Just like polynomial inequalities, we'll have that. But we also have another requirement to make sure that the denominator of these rational expressions is never 0. So that adds another layer of critical values or boundary solutions to the numbers that we have to find. Okay? So we have what we've been doing, we have that. In addition to that, another layer that will contain any values that would make the denominator of these rational fractions equal to 0. We need to know what they are, and we need to exclude them from the final solution. In this case, this expression will never be 0, right? It will never be 0, even though it is allowed to be equal to 0, and it is allowed to be less than 0. It'll come awfully close to 0, as a matter of fact, infinitely close to 0, but it'll never be 0. So what else then we have to look for? Look for any critical values that would make the denominator equal to 0, and that's easy to find, right? X minus 3 equals 0, so x equals 3. So that's a critical boundary solution, okay? All right, so that means our final solution cannot include that because it's making the denominator 0. So let's draw the graph here. X equals 3 would be somewhere here, and I'm going to put a hollow circle here, 3 and dashed lines over it, indicating that 3 itself is not part of the solution. So how many regions should we check? 2 regions, right? One is this region, and one is this region. In each region, let's pick the easiest number possible. On the left, let's pick 0. So test x equals 0 on the left, right, in this region. We're going to plug that into this rational inequality right there. So 1 over 0 minus 3 less than or equal to 0, that is, let me move this up a little bit. So we're going to have that left side simplifies to minus 1/3 less than or equal to 0. Is this a valid result? Yes. minus 1/3 is less than 0. So this checks out. So we say yes, all of that region is part of the solution. Let's then let's check a number, easy number in this region. Let's check test equals 4. Okay, we're going to plug into that. So 1 divided by 4 minus 3 less than or equal to 0. And that's 1 divided by 1 less than or equal to 0, or 1 less than or equal to 0. Is this a valid result? No. No. So that region is not a solution region. Okay. I know we haven't found, or we haven't yet gone through an example where both sides check out, but the middle, that number doesn't check out because it makes the denominator 0. But there are various solutions. You might in fact find one solution where everything is part of the solution except the number that makes the denominator equal to 0. Okay? So what I'm saying is that just because we have yes and no, or sometimes no and yes, it doesn't mean that it's always like that. It's not always like that. It's just case by case. We have to investigate it to be sure which regions are part of the solution. Okay? So giving us this result, then we can write this final solution. Of course, using the interval notation, which they ask here. Okay, so the solution is minus infinity, parenthesis, minus infinity, 3 bracket or parenthesis, which one? Parenthesis, right? 3 itself is not cannot be part of the solution because it makes the denominator equal to 0. Okay, so this second one, this would be a good time for you to please pause the video, find the solution of that inequality, and according to your own thinking and skills at this moment, and then come back to the video. Okay? So I don't want you to sit there and just watch this video like you would watch a movie. Okay? This is not the way to benefit from these movies. I've said this before, but I want to remind you, I want you to build very strong set of skills moving through this course. Not even a strong, very strong, and this is the way to do it. You got to get involved and solve all these problems before you see the solutions put on the board or on the screen by somebody else. Okay? All right. So I'm assuming you've done that, and now you're back. Here, we have two situations. One, we can have this expression equal to 0, which is whenever 5x equals 0, that whole expression is equal to 0. Or we can have another critical value because the denominator can never be 0. So let's find both critical values. So if 5x equals 0, that will make this whole fraction 0. So there, from that, x is equal to 0. So that's one of the critical values. The second critical value is any x value that would make this fraction undefined. When does that happen? Whenever x plus 1 equals 0. So if x plus 1 equals 0, then x equals -1. So 0 and -1 are the two critical values. Okay? So let's draw the real number line here. And let's plot these values. So can this expression be equal to 0? No, it can't, because look at this. This is a strict inequality. A strict inequality means the left side cannot be equal to the number that appears on the right, in this case 0. So x equals 0 is not acceptable. So I'm going to put a hollow circle on top of it, on top of 0, and put a dashed line over it. So 0 is excluded. What about negative 1? Negative 1 is also excluded. Why? Because it would make the whole thing undefined. Right? The first one would make it equal to 0, and we can't have that. We cannot have the left side equal to 0. Otherwise, we would have an equality under this. The second, negative 1, the second number should be excluded because it will make this undefined. So also, once more, I'll put a hollow circle over negative 1 and a dashed line on top of it. So we have to test 3 regions, this region, and this region. I hope so far this is similar to what you've been doing in your own solution. Okay, I hope so far we agree. So now let's test an easy number in each of these 3 regions. So we want to test x equals negative 2. Let's plug negative 2 into this original rational inequality. So we have 5 times negative 2 divided by negative 2 plus 1 less than 0. Let's do the algebra on this. We get negative 10 divided by negative 1, 0, and then positive 10 less than 0. Is that a valid result? No, right? Positive 10 is not less than 0, so no. This region from which we picked this test x value is not a solution region for this rational inequality. Let's pick a number in between negative 1 and 0. Let's pick 0.5, right? Or 1/2, negative 1/2. So test x equals negative 0.5, right? In between these two, in that middle region. So plugging in, we have 5 times minus 0.5 divided by minus 0.5 plus 1. So in the numerator, we have minus 2.5, right? But let's double check. 5 times minus 0.5 is minus 2.5, right? So minus 2.5 divided by minus 0.5 plus 1 is positive 0.5. Is this left side less than 0? Absolutely, it is. It's a negative number. So the middle region here, yes, that's acceptable solution region. Let's pick another test point here, something easy. Let's test x equals 1, right? Right in this region, 1. Plug the 1 inside this expression. What do we get? We get 5 times 1 divided by 1 plus 1 less than 0. So we get 5 over, oops. Sorry, let me correct that with my thick pen here. So we get 5 over 2, right? Less than 0. Is that a valid result? That's positive 2.5. Is positive 2.5 less than 0? Absolutely not, right? So that is not a valid result. So no, that is not a solution region. So where is the solution region? The solution region is in the middle, in between negative 1 and 0, not including negative 1 and 0. So negative 1 parenthesis, negative 1 comma 0 parenthesis, like that. Okay. So I hope this is making sense. Next, please go ahead, write down that expression, find the solutions of this rational inequality, and then come back to the video after you've given yourself the chance to think and write down the solution for this. Okay, please do that. Okay, I'm assuming you've done that, and now you're back. So the first thing we would do is we need to find factors of the left side, or all the values that would make the left side equal to 0 or undefined in this case, right? So what we would need to do is combine these two fractions into one. So the common denominator, right? The common denominator here would be x minus 2 times x minus 1. Now, to take the common denominator between these two, then multiply each numerator by what's missing from its denominator when you compare that with the common denominator. So here, we would multiply x plus 1 by x minus 1. Why? Because x minus 1 is missing from that denominator. So x minus 1 times x plus 1 minus. Multiply this numerator by the term that is missing from its denominator when you compare it with the common denominator. That would be x minus 2. Okay, less than 0. So now we got to simplify the numerator. The denominator is happy because it's in factored form. We're okay with this. But let's simplify the numerator. So that one we get x squared minus 1. And then we have minus x squared. I'm going to FOIL this. X squared minus 3x minus 2x plus 6 divided by all of that, x minus 2 times x minus 1. Then let's distribute this minus into all of that. What do we get? We get x squared minus 1 minus x squared, positive 3x, positive 2x, right? We're just distributing this into that. Minus 6 divided by x minus 2 times x minus 1. Like that. Now let's simplify the numerator a little bit, right? X squared and then minus x squared cancel each other out. So then we have 3x plus 2x, that's 5x. And so 5x minus 6 minus 1, that is minus 7, right? Divided by x minus 2 times x minus 1. Less than or equal to 0. Like that. Okay, now with this form, we can easily find what numbers make this expression 0 and what numbers make this expression undefined. So can this left side be equal to 0? No, because notice the equality is missing, right? This is a strict inequality, meaning that the left side must be less than 0, not equal to 0. Okay, having said that, let's find the critical values. 5x minus 7 equals to 0. That means 5x equals 7, right? Minus 7, move it to the right, it becomes positive. And then x is equal to 7/5, which is something greater than 1. 1 point something, right? Then x minus 2 equals 0. Then from that, x should be equal to 2. And of course, x minus 1 equals to 0, so which means x should be equal to 1. So we have these three critical values, 7/5, x equals 2, x equals 1. Okay, let's graph these. And we're going to use this inequality to plug into and to test each value. So I'm going to have to scroll up here to use this space. So here's our graph, negative infinity to infinity. These three numbers plot all on this side. So we have a hollow circle for 1, hollow circle for 2, and a hollow circle for 7/5, which should be somewhere here. Okay, so that's dashed line for all of those, like that. So how many regions should we check? 1, 2, 3, 4 regions. Or let me use a different color because I used red to draw my dashed lines. Okay, those 4 regions should be checked. Let's check here in this inequality. So test x equals some easy number here, 0. Okay, let's test that. In here, we have 5 times 0 minus 7 divided by 0 minus 2 times 0 minus 1. Then we have 0 minus 7. 0 minus 7 divided by minus 2 times minus 1, that's positive 2, less than 0. Is this a valid result? Yes. This is, in fact, a valid result because minus 2 times minus 1 is positive 2. So minus 7 over 2 is a negative number. So yes, in that region, it checked out. Let's test some number between 1 and, let's say, 7/5. This was 7/5, right? So 7/5, what is that exactly? It is 7 divided by 5, 1.4. So if that's 7/5 is 1.4, so 1.2 would be between 1 and 7/5, right? So let's test x equals 1.2. Plugging into this inequality here, we have 5 times 1.2 minus 7 divided by 1.2 minus 2 times 1.2 minus 1, and we want to know if that side is less than 0, right? So that's 5 times 1.2 is 6, positive 6. 6 minus 7 is minus 1 divided by 1.2 minus 2 is minus 0.8 times 1.2 minus 1 is 0.2. So this is going to be, the denominator is going to be 0.16. I'm testing it here, so yes. So this will be positive, right? Minus divided by minus is positive 1 over 0.16. Is the positive number less than 0? No. So right here, we write no. Okay? So between 7 over 5, which was 1.4, and 2, let's pick 1.5, right? Would be between 7 over 5 and 2, and test that. I'm quickly running out of room here, so let me put that, if you don't mind. Well, maybe I can fit them all in here. I think I can. Let me draw this line so it doesn't. So I'd rather put this in order at the bottom of this. So let's test like that. Let's test x equals 1.5. Okay, so we're going to plug in here 5 times 1.5 minus 7 divided by 1.5 minus 2 times 1.5 minus 1 less than 0, right? So 5 times 1.5 is 7.5 minus 7, that's 0.5, divided by 1.5 minus 2 is minus 0.5. Minus 0.5 times minus 0.5 times positive positive 0.5, it's minus 0.25, less than 0. So this is, it doesn't matter what that value is exactly, but what matters is that this whole left side is minus, is a negative number. So is it less than 0? Yes. So for this region, yes. Between 7/5 to 2 is the solution region is acceptable. So one more region to test, which would be after 2. So let's pick test value equals 3. So test x equals 3. And we're going to plug in here, just like before. 5 times 3 minus 7 divided by 3 minus 2 times 3 minus 1 less than 0. So what do we have? We have 5 times 3 is 15, minus 7 is positive 8, divided by 3 minus 2 is 1, 3 minus 1 is 2, both positive. 1 times 2, positive 2 is 2, less than 0, so 4 less than 0. Is that result acceptable? Let me move this up a little bit. Is 4 less than 0? No, that result is not acceptable. So this region is no solution. So the only solution region is from negative infinity all the way to 1, excluding 1, union between 7/5 and 2. Okay? So let's write that down. Negative infinity, comma, 1, parenthesis, union, parenthesis again, 7/5, comma, 2. Like that. Okay? So I hope this made sense. And I can barely fit everything on the screen, but that was the expression we began with. Okay? Here you can see all the solution on the screen at once. And if you can follow how the solution begins by, first of all, taking the common denominator and then factoring and simplifying the terms on the left, and then finding the critical values and then testing number in each region, then the whole thing should make sense. Okay? Okay, so next one is this example here. So if you haven't done this already, please make sure that you pause the video and you find the solution of that expression, and then come back to the video to compare your solution with mine. Okay, I'm assuming you've done that, and now you're back. Okay, so the first thing is move everything to one side and set the other side equal to 0. So we can say 4 minus 4 over x minus x greater than or equal to 0, right? What should we do next? We should take the common denominator. The common denominator is x, and the denominator here is 1, the denominator here is 1, right? Compare their denominator with the common denominator and multiply the numerator by what's missing from their denominator when you compare it with the common denominator. So here x is missing from that, so we multiply 4 by x, 4x. Here x is present and it's equal to the common denominator, so no change. We simply write down that numerator. Here again x is missing from this denominator, so multiply the numerator by the missing term, minus x squared greater than or equal to 0. Okay, the red ones are just denominators of x and 4 from the previous inequality. Okay, so now we want to make sure that we factor the numerator. Let me put these terms in order. We have negative x squared plus 4x minus 4 divided by x greater than or equal to 0. Okay? To begin with, you could have put 4 on that side. You could have kept 4x plus x and then minus 4 and then gone that route, so to speak. And you would, it's perfectly valid to do that, and you would end up with the same result as, in other words, our answers would agree. So it doesn't matter. You could have just moved 4 to the other side rather than bringing these two terms on this side like I did. It makes no difference. But the point being, you gather all the terms on one side and the other side is going to be 0, greater than or less than or equal to 0, depending on which way you go. So for me, it turns out that the left should be greater than or equal to 0, okay, which is fine. All right, so let's factor the numerator here. The denominator is okay. We know x equals 0 is going to be undefined, so we already know x equals 0 should be excluded from the solution for this rational inequality. But the numerator still is a mystery. We don't know the factors of it, so we don't know what makes it equal to 0. So let's find out. We're going to factor this. Minus x times x, x squared. So what two numbers would add up to, or multiply to negative 4, negative 2 plus 2, and add up to positive 4x? So this should do it. Negative x times x, negative x squared. Negative x times minus 2, that's positive 2x, plus positive 2x, that's 4x. Then minus 2 times 2 is minus 4. So we got it. So that divided by x greater than or equal to 0. Okay. So now we have the numerator in factored form. The denominator is obvious what makes it equal to 0, which is something we want to exclude from the final solution. So let's write these down. So the critical values are as follows. Negative x plus 2 equals 0. Then negative x equals negative 2. Then x is equal to 2. Okay. Then x minus 2 equals 0. Therefore, x equals 2 again. Right? And then finally, x equals 0 in the denominator. So all of these three values, well, all of these two values, right? X equals 2, x equals 2, that's the same value, and then x equals 0. All right, so let's plot these on a real number line and then pick out test values. So can the function accept, well, we're going to plug here. This is what we're going to plug our test points in. Can this x take on x equals 0 value? No, because that would make the function undefined, right? So I'm going to put a hollow circle on top of 0, right? A hollow circle. And a dashed line, of course. Okay, so 0 is excluded from the final solution. What about 2? Right? 2 is okay because it's going to make the left side equal to 0, which, is it okay? Yes, it's okay because as this symbol indicates, the left side can be greater than or equal to 0. So it could be equal to 0 or some positive value. Okay, so 2 would be, let's say, here, and I'm going to put a filled-in circle for that and a solid line on top of it. So 2 can be and will be included as part of the final solution. So we have three regions to check: this region, and this region. All right. Let's test values in this one. Okay. So we're going to test an easy number there. Would be x equals minus 1. Let's plug in. We have minus 1, positive 1, right? Plus 2, minus 1, minus 2. divided by minus 1. We're asking if that left side is greater than or equal to 0. So we have minus 3 here times positive 3, that's minus 9, divided by minus 1, greater than or equal to 0, or 9 greater than or equal to 0. Is this a valid result? Yes, that's a valid result. So this region is part of the final solution. Now let's pick a number in this region. So test an easy number like 1. Let's plug in here. So minus 6 would be minus 1 plus 2 times 1 minus 2 divided by 1, right? We're asking if that side is greater than or equal to 0. So we have minus 1 plus 2 is positive 1 times 1 minus 2 is minus 1 divided by 1. And this is negative 1 greater than 0. Is that a valid result? No, right? So this region is not a solution region. Okay, let's test an easy number in this region, such as x equals 3. And we're going to plug in here. So minus 6 would be minus 3 plus 2, 3 minus 2 divided by 3. Greater than or equal to 0, we want to know that. So this is going to be minus 3 plus 2, that's minus 1. 3 minus 2, that's positive 1. Divided by 3, greater than or equal to 0. And let's see, so we end up with minus 1 divided by 3 greater than or equal to 0. Is that result a valid result? No. So again, no in that region. Okay, let me see, let me double check this. So we picked negative 1 here, and negative 1 here would be positive 1. I'm just double checking just to make sure that everything is okay here. A positive 1, 3 times negative 3, negative 9 over negative 1, that's positive 9, greater than 0, so we're okay there, yeah. X equals 1, so that was, what did that give us? They gave us 1 from here, negative 1 plus 2, that would be positive 1, times positive 1 times negative 2, that would be negative 2. So positive 1 times negative 1, that would be negative 1 over 1. So it would not check out. And also this one, x equals 3, plugging in negative 3 plus 2, 3 minus 2 over 3. So that's negative 1, positive 1, and 3. Yes, that's okay. So then the solution region in this case is really strange, because we have negative infinity to 0, and 0 is excluded, and then we have a 2 by itself that can give us what we want, the result that we want, right? So the final solution in this case is, let me write it here. So there, that's the entire solution. And I'm going to put the final solution in this box right here. Well, let me write it here. So it'll be negative infinity to 0, parenthesis, right? Because 0 is not included. Union just this 2, because both sides of it do not check out, but the 2 itself does check out. So curly brace 2 like that. Like that, okay? So that is the entire solution for that problem, showing on the screen like that. Okay. All right. So the next problem, once again, we have to put everything, before I forget, please make sure that you pause the video and find a solution for this before you see my solution. Okay, that way it'll be a very productive lesson. Okay, so I'm assuming you've done that and now you're back. So the way we approach this is we can factor both sides. Let's do that, and then move everything to one side. Either way, it makes no difference. So we have 3 over x plus 2 times x minus 2, because x squared is minus another perfect squared term. A perfect squared term minus a perfect squared gets factored into this term, 2 terms. This is a special, one of the 3 special product formulas that I've asked you guys to memorize. Okay, it keeps paying dividend after dividend if you've memorized it. Those 3 are very useful. Which 3, you might ask? If you're asking which 3, let me write that on a piece of paper again, just as a reminder. These are the 3 special product formulas I'm talking about that you should memorize. A plus b squared is equal to a squared plus 2ab plus b squared. A minus b squared is a squared minus 2ab plus b squared. And of course, the one that we're applying here is, well, if you have x squared minus y squared, that gets factored into x plus y times x minus y. These 3. These 3 are very useful special product formulas. All right? So in this case, we are applying that, the one in red, that I showed in red, to this one. And on the right, let's see, the denominator can be factored, right? And those are easy numbers to factor. So x plus 5 times x plus 2 are the factors of that. Now let's move everything to one side. What do we have? We have 3 divided by x plus 2 times x minus 2 minus 5, right? Minus, because it was positive on the right, positive 5 over this, x plus 5 times x plus 2. And on the right, we have less than or equal to 0 after we move it. So positive on the right, when we move it to the left, it becomes negative. Okay, so now we need to have the common denominator here. So the common denominator would be each factor in the highest power it appears. So all of these have power 1. So x plus 2 and x plus 2, it appears in the common denominator only once, right? X plus 2 once. Then x minus 2, then x plus 5. So now we have each factor appearing in the common denominator only once. And it appears in the highest power, which in this case is just 1. Okay, now compare this denominator, common denominator, with this denominator. What factor is missing from this when you compare this with this? X plus 5, right? So multiply 3 by x plus 5, by the missing term from the denominator. Like that. Minus, minus, right? 5, 5. Then compare this common denominator with that denominator. What is missing from this denominator? X plus 5 is there, x plus 2 is there, but not x minus 2, right? So multiply 5 by the missing denominator, the missing factor from the denominator. So x minus 2. Less than or equal to 0. Now, then let's distribute this. The denominator is fine because it's in fully factored form, which we want. But the numerator, we need to distribute and simplify terms, right? So let's do that. So 3 times x is 3x. 3 times 5 is positive 15 minus 5x plus 10 divided by all of that. X plus 2 times x minus 2 times x plus 5 less than or equal to 0, right? So let's simplify the numerator a little more. 3x minus 5x minus 2x. 15 plus 10 plus 25. All of that divided by x plus 2 times x minus 2 times x plus 5 less than or equal to 0. Great. Now we can list all the different critical values. Let's write it up here this time. Maybe I'm trying to keep everything on the screen. That's why I want it like that. So let's come up from here to here. So minus 2x plus 25 equals to 0. That means minus 2x equals minus 25. That means x equals negative 25 divided by negative 2. It'll be positive 25 divided by 2. So that's one of the critical values, right? 12 and a half. 25 over 2 is 12 and a half. Then each of these factors in the denominator, right? None of these can be 0. So we got to be very careful. So before we do that, let me ask you this. Can the final solution include x equals 25 over 2? Can it include that? Yes, it can. Because this whole thing is allowed to be equal to 0. Look at that. It's allowed to be equal to 0. So 25 over 2 is acceptable answer or solution. But from this point forward, minus 2 plus 2 and minus 5 will not be able to be part of the solution because each of those three will make the denominator 0 and the function undefined. So let's keep that in mind as we're moving forward with this solution. So x plus 2 equals 0, then x equals minus 2. Right? That's another critical value. Then x minus 2 equals 0. We get x equals 2. That's another critical value. X plus 5 equals to 0. Then x equals negative 5. Right? Like that. All right, so therefore, we have been able to find our boundary solutions. Let's plot them. So we have negative 2 and negative 5. Let's say that's negative 2, and we have to put a hollow circle there. Then negative 5, another hollow circle there. Right? Negative 2, negative 5. I'm going to put a dashed line over each one. Then we have the 2 also with a hollow circle, right? And then finally 25 over 2, which is allowed to be part of the solution, or 12 and a half. So that with a solid line on top of it. So how many regions should we check? 1, 2, 3, 4, and 5 regions we need to check. Okay? I hope I have enough space here to do that. So I'll try to write the solution in more compact form so I can fit everything here. Let's pick an easy number here. Let's take x equals minus 6. And we're going to put all of that in this inequality. Okay, not that one, this one. Okay, so minus 6 times minus 2, that's positive 12. Plus 25, that's 37. Right? 37, positive 37. Minus 6 plus 2 is minus 4. Minus 6 So minus 4, minus 6, minus 2, that's minus 8. Let me move this up a little bit. So minus 6 plus 2 is minus 4. Minus 6 minus 2 is minus 8. Times minus 4, that's positive 32. Times another minus 1 from this. Minus 6 plus 5 is minus 1. So minus 32. Is the left less than or equal to 0? Absolutely. Right? So this checks out. So in this region we have yes. We have solution there. Let's test between some easy number between negative 5 and negative 2. Let's test x equals negative 3. Plug that in here. We have, let's see, minus 3 times minus 2, that's positive 6. Positive 6 plus 25, that's 31. Positive 31. Positive 31 divided by, put minus 3. Put minus 3 here, you get negative 1. Negative 1 times negative 3 minus 2, that's minus 5. Negative 1 times minus 5, that's positive 5. Positive 5 times negative 3 plus 5, that's positive 2. So we get positive 10. Right? Let me make sure one more time. Negative 1 times negative 5. No. Yeah, the negative 3, that's negative 1. And then negative 5, that's positive 5 times 2, 10. Yes, positive 10. Is that less than or equal to 0? No. No. So here, we have no solution in that region. Now let's pick a number between negative 2 and 2. Easiest number would be 0. So test x equals 0. Right? Between negative 2 and 2. And we're going to plug it in here. So negative 2 times 0 is 0, plus 25, that's just 25. 0 plus 2 is 2, times 0 minus 2, that's minus 2. 2 times minus 2 is minus 4. And then minus 4 times 5, that's minus 20. Is that less than or equal to 0? Yes. So yes, we end up with yes. Okay. So we have, then let's pick a number, easy number between 2 and 25 over 2. An easy number would be 3. Right? Test positive 3, right? X equals 3. Plugging in here, we get negative 6 plus 25, that's 19. Right? Positive 19. Then we have 5 times minus 1 times 1, that's positive 5, times positive 8, that's 40. Right? One more time. 5 times 5 times 1 is 5, times 8, 40, positive 40. And then less than or equal to 0. Is 19 over 40 less than or equal to 0? No, because this is a positive number. So no, that region is not a solution. So 25 over 2, we know it's part of the solution, but that's 25 over 2 is 12.5. So anything above that would be, let's pick an easy number, easiest one. Test x equals 13. So test x equals 13. The other numbers are bigger, right? So I picked the smallest one. So in here, minus 2 times 13 is minus 26, plus 25, that's minus 1. Divided by 13 plus 2, that's 15, times 13 minus 2, that's 11. 13 plus 5, that's 18. Right? So 15 times positive 11 times 18. Okay, great. So this whole thing is going to be a negative number, irrespective of what that number is, right? Because of this minus, this whole thing is negative. So yes, that region, x equals 13, that far right side is also part of the solution. Okay, so the solution regions are these. Let me highlight them. This region is a solution, that one, and that one. Okay, so let's write it up. From negative infinity to negative 5, right? Parenthesis or bracket. Negative 5 is not included, right? Remember, it's going to make the denominator 0 and this function undefined. So parenthesis to exclude negative 5. Then union, negative 2 will also make this expression undefined. So parenthesis negative 2, comma, 2 the same way will make this denominator 0, parenthesis, right? That's for that from here to here. Then the last piece, right? Union. 25 over 2 is allowed, is an allowed x value. So bracket 25 over 2, comma, infinity parenthesis. Okay? Like that. Okay. So here, I hope this matches what you had in your own solution. Like that. All right. The next expression, again, please pause the video. Right there, pause the video, write your own solution for that rational inequality, and then come back to the video and see what I've done. Okay, I'm assuming you've done that, and now you're back. So the first thing I would do is move everything to one side and set the other side equal to 0. So 4 divided by, because my space is limited, at the same time I'm doing this, let me factor the denominator as well. Right? Let's do that. So that's x plus 3 times x minus 3. And then minus, right, minus, moving that to the other side, we have 3. This is also a perfect square minus another perfect square, so we have x plus 5 times x minus 5 less than or equal to 0, right? Okay, so the common denominator here would be each of these factors in the lowest power that it appears, that it has, right? So we have x plus 3 times x minus 3 times x plus 5 times x minus 5. And then less than or equal to 0. But now each numerator gets multiplied by what's missing from its denominator when you compare it with the common denominator. So 4 multiplied by these two. So x plus 5 times x minus 5. Minus is minus. This numerator 3 is going to get multiplied by what's missing from its denominator when you compare it with the common denominator. So minus 3 times x plus 3 times x minus 3. Okay, those two terms, and I should have written them in red, I forgot. Those two factors are missing from this denominator, so 3 gets multiplied by them. Okay, so let's distribute and simplify. In the numerator, we're going to have, again, I'm going to make this a little bit compact so I can fit the solution here. So we have 4x squared minus 100. And here we have minus 3x squared, multiplying these, and then minus 9 times plus 27. Okay, that was x squared minus 9. And then times, yes, okay. So all of that divided by these series of factors. Less than or equal to 0. Okay, simplifying the top portion, we have 4x squared minus 3x squared, so we have just x squared. Minus 100 plus 27, so what do we get? We get minus 73, right? Minus 73. All of that divided by, let me make sure, so, right? So 100 minus 27, so that's correct. Divided by all these factors, so x plus 3 times x minus 3 times x plus 5 times x minus 5, less than or equal to 0. Okay, so let's find what makes this expression undefined and what makes this expression equal to 0. So if the numerator is equal to 0, the whole thing is equal to 0. Is that allowed? Yes, because of this equality, we are allowed to have this expression be equal to 0. So when does that happen? Is when x squared equals, well, let's find that out. So from here to here, x squared minus 73 equals 0. So that means x squared equals positive 73. So that means x squared, or x, is equal to plus or minus square root of 73. Let's see what that number is. So I'm going to calculate that here. So we have a rough idea where that is located on the real number line. So square root of 73, 8.54, right? So roughly, so this is x roughly equals plus or minus 8.54. So the other factors in the denominator make it easy for us to determine where are the critical values, right? I apologize, but in order to save space here, I'm just going to write down those critical values, okay, without the usual details that I use to write these answers. So the other x values are x equals negative 3, right? X equals negative 3. X equals positive 3. X equals negative 5. And x equals 5, right? So the real number line we have negative 5, negative 3. So negative 5, negative 3, and then we have also negative 8.542. So that will be way out here, and that is allowed. So negative square root of 73. So that is a solid line, that is a dashed line. And then negative 3 also. So then -5, -3, what else? And 3 and 5, and positive 8.5, right? So we have the positive 3, positive 5, and the positive square root of 73. So where are the regions that we should check? We need to check this region, this region, this region, this region, here and here. 1, 2, 3, 4, 5, 6, 7 regions to check. So let me use a scratch paper here, because you can see how much space I have left, right? So I'm going to use a scratch paper to test all of those here. Let me write this down so we have everything on the screen. When I have the final result, we'll come back to this and write the final solution. But let me write this down. So we have x squared minus 73 divided by x plus 3 times x minus 3 times x plus 5 times x minus 5 less than or equal to 0. And okay, so that's that. So this is just a scratch paper on this sheet. I'm not going to post this. What I'm saying is that I'm not going to post this on Canvas because I'm using it as a scratch paper. But I will post this final result once we're done with it, right? Okay, so let's test some number. Let's test some number to the left of negative square root of 73. So it would be -9, right? Because negative square root of 73 is negative 8.554. So -9 would be roughly to the left of that. So test x equals -9. So -9 squared is positive 81. Minus 73, that's positive 8, right? Positive 8. Divided by -9 minus 3, that's -6. Negative 9 plus 3 is -6. -9 minus 3, that's -12. -9 plus 5, -4. -9 minus 5 is -14. So what we're looking for is not the exact value, but whether this number is positive or negative. You multiply all of this by each other, you have 4 negative numbers being multiplied by each other, right? So the result is going to be positive. Okay? So because this whole thing is positive, it's not possible for the left to be less than or equal to 0. So no. So that region, when I had that question mark, so let's write no. Okay. Now let's check a number between negative 8.54 and -5. So -6. Okay. So test x equals -6. -6 squared is 36, right? And then 36 minus 73, right? That. 36 minus 73 is minus 37. Divided by, plug in -6 in each of these. -6 plus 3, -3. -6 minus 3, -9. -6 plus 5, -1. -6 minus 5, -11, right? And the question is the left side less than or equal to 0? So we have 4 negative numbers multiplied, these will be multiplied to a positive value, and then we have minus a negative number, so divided by a positive, which is negative. So yes, this checks out. Okay, so let's go back to the graph. So here, between negative square root of 73 and negative 5, yes. Okay, so let's pick a number between negative 5 and negative 3. Let's say negative 4, right? So we're going to test. We're going to test negative 4. So negative 4 squared, we're plugging in here, right? That one. Negative 4 squared is positive 16. Positive 16 minus 73 minus 57 divided by negative 4 plus 3 is negative 1. Negative 4 minus 3, negative 7. Negative 4 plus 5, positive 1. Negative 4 minus 5, minus 9. And we ask if the left side is less than or equal to 0. So 3 negative numbers multiplied by each other, we get a negative number. But a negative number divided by a negative number is a positive number. So this is no good. So x equals negative 4 is not, so that whole region is not part of the solution. So no. Okay, let's pick an easy number in this region from negative 3 to 3, which would be 0, right? That's the easiest number. So let me do that up here. Up here, so test x equals 0, right? So 0 squared is 0, minus 73 is minus 73, divided by 0 plus 3 is 3. 0 minus 3 is minus 3. 0 plus 5 is 5. 0 minus 5 is minus 5. Is the left side less than or equal to 0? Well, minus times minus is positive, but then we have a negative number divided by a positive quantity, so it's the overall result is negative. So yes, that will work. So going back to our graph, yes, this region is a solution. So now let's pick a number between 3 and 5, positive 3 and 5. So positive 4, right? So test x equals positive 4. Let's plug in there. So 4 squared is 16, minus 73 is minus 57, just like this, divided by 4 plus 3 is 7. 4 minus 3 is 1. 4 plus 5 is 9. 4 minus 5 is minus 1. Is the left side less than or equal to 0? No, because negative divided by a negative number is positive. So no. So we come back here and we say that for this region, between 3 and 5, there is no solution. Okay. Between 5 and positive 8.54, right? So 6. So let's test x equals 6, right? Okay. So plugging in, we have 36 minus 73, so that's minus 37, divided by positive 6 plus 3, that's 9. Positive 6 minus 3, that's positive 3. Positive 6 plus 5, 11. Positive 6 minus 5, 1. is the left side less than or equal to 0? And the answer is yes. That left side is negative number as a whole, so this checks out. So going back to our graph here, between 5 and positive 8.54, yes. So that's also a solution. So we have to check right after positive square root of 73. Let's pick 9, right? So testing like that. So test x equals 9. So 9 squared is 81 minus 73. It is 8, positive 8, right? Divided by 9 plus 3 is 12. 9 minus 3 is 6. 9 plus 5 is 14. 9 minus 5 is 4, less than or equal to 0, right? All these numbers are positive. Positive divided by positive, it's a positive result. So is this a valid inequality? No. A positive number is not less than or equal to 0. So we'll go back to the graph and we say that no, that region is not part of the solution. Okay, so now we can write down the final solution using the interval notation. So here we have from bracket, right? Because negative square root of 73 is part of the solution. So negative square root of 73, comma, to negative 5, but negative 5 cannot be part of the solution. So we have to have a parenthesis here. And let me highlight this so that this is the expression inequality, rational inequality for which we are finding the solutions, right? So all of this is the solution of that. Okay, union, that region is not a solution. How about between negative 3 and 3? Yes, that's a solution, but excluding negative 3 and 3. So which means those numbers get the parenthesis. Parenthesis negative 3, comma 3, parenthesis, union. Then that region is not a solution, but this region is a solution. That region, something interesting happens because 5 is not part of the solution. Why? Because it would make the denominator equal to 0. We know that in here and in here. So we don't want 5, so parenthesis 5, comma, positive square root of 73 is part of the solution, right? Because it would make this expression equal to 0, which is fine. We're okay with that. So square root of 73 bracket, okay? So that is the final solution for that expression, okay? So it's critical. I'm sure you've seen that all of this section is most of this class is very, very procedural. So you will get exceedingly excellent at carrying out this procedure if you do your own solutions, you prepare them before you watch the videos, or you look at the solutions in the book. And that way you will become a true master of this subject, because procedure is something that you repeat more, the better you get at it. I want to thank you for persisting through this video, and for now, have a very nice day, and I'll see you again next time.